In this video, I want to derive a formula to find the distance between 2 points in R3. After that, we'll talk about how to find the midpoint between those 2 points. So let's just assume I have 2 points in space, and I've drawn them here on the board in a right-hand coordinate system. And so I have one point labeled x1, y1, z1, another point labeled x2, y2, z2. And I want to make the assumption for right now that all three in the pairs, at least, are different. And what I mean by that is x1's different than x2, y1's different than y2, and z1's different than z2. And in this way, I could actually think about those 2 points lying on opposing ends of the long diagonal in a rectangular prism. And I don't have a rectangular prism, but I do have a cube. So we'll just pretend that this is a rectangular prism, because I have no guarantee here that the side lengths would all be the same. But let's just say I start back here at z1, x2, y2, z2, and imagine it being that. To get to this point where all of the numbers in it are different than these, right? The z-coordinate would have to change, so I'd either have to go up or down. I'm just going to pretend I have to go down. The y-coordinate would have to change, so I can't be here. I have to go this way, and the x-coordinate would have to change. And there I am, those two opposing corners of that rectangular prism. So I'd like to add a rectangular prism to my diagram. So now think about starting at this point. Right, to get to that one, it's like the y-coordinate would have to change, so I go some distance in the y direction. Right, the z-coordinate changes, so I have to go some distance z. Remembering that when I draw these things, I'm going parallel to an axis. Right, and then I'm going to complete what I would think of as the front face of that rectangular prism. Right, and I can imagine doing the same thing back here, that the z-coordinate would have to change and the y-coordinate would have to change. And then I'd have the same change in z, and I might have to, amend my diagram as I go, but now I want to imagine the x-coordinate changing. And now I'm starting to see that rectangular prism with those 2 points on its, as far apart as they can go on opposite ends of that long diagonal. So that's the distance I'm trying to find, right? The distance between those 2 points, d, right? I want to find that length. The length of that long diagonal will be the distance between my 2 points. And so what I'm going to do is actually form a right triangle. Because if I think about this rectangular prism, I could draw a diagonal on the floor, which would make a right angle with this side. So I'm going to call this length down here L. Because what I can observe is that in this right triangle, the Pythagorean theorem would certainly have to hold. And I can actually find this distance, right, because I have 2 z-coordinates to think about. And so preliminarily, I can write down that d squared is equal to L squared plus this distance squared. Well, that distance would be the difference in my z-coordinates. So if I can find an expression for L in terms of x1, y1, and z1, I'd be done. Nicely enough, I only need information about x's and y's to fill in that blank, and then I'll solve for d. So now I want to look at this right triangle that would be on the floor of my rectangular prism, right? Whose hypotenuse would be L, and then I have these side lengths. And so let's talk about this point and this point. This point back here is directly under this one. So the only difference between these 2 points is the z. So that point back there would be x2, y2, z1, right? Because z1's the height of the bottom of my rectangular prism. All right, so now if I look at this point, well, it is a change in y different than this point. It's still in the floor of the shoebox. It's still in the front of the shoebox, thinking about that rectangular prism as a shoebox. And I only changed that information about y. So I have x1, comma, y2, comma, z1. So now I can talk about the changes in length on the sides. right, looking at this point, the only thing that changes y All right, this distance would be y2 minus y1. I'm gonna put in absolute value because I'm kind of assuming a left to right here in my particular picture, and I want this formula to work for any points, right? So I'm gonna not assume anything about which one of these y values is larger. And then looking at these 2 points, the only thing that changes between them are the x values. Right, so I get that in absolute value. All right, so well now L squared is equal to this distance squared plus this distance squared. Since I'm squaring them, I don't need the absolute values. And now I'm ready to substitute this in for L squared because, well, that's what L squared is. And this will give me my distance formula. Let x1, y1, z1, and x2, y2, z2 be any points in space. Then the distance between them is. And I had a formula for d squared, so I'm going to go on and take the square root. It's a distance, so I only need the positive square root. And then it would be L squared, which I know is the same as x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And what's really nice about this distance formula is that it looks a lot like my distance formula from points in the plane. If I cover up the bit about z, I get an expression that finds the distance between 2 points in R2. So what I really have here is a distance formula for R3. In R2, I remember that my distance formula looked like this. And so this is a nice generalization. What it basically says is, hey, do the same thing you did before, but add a term under the square root for the z direction. And so now I'm wondering if there was secretly a formula for distances in R1 that kind of looked the same. And this is almost silly, right? But x1 and x2 on a number line, what you really learned is that distance formula was the absolute value of x2 minus x1. If I know which one's bigger, I just do the subtraction, but in the most general sense, I take an absolute value. And if I just think about it for a minute, that's really the same as taking the difference between x2 and x1, squaring it, and then taking a square root, which fits this general pattern. So really, the idea of distance that we had all the way down to R1 is what really holds true all the way through R3. Okay, at the beginning of the video, I promised you a midpoint formula, so here it is. I have 2 points in space, x1, y1, z1, and x2, y2, z2. And I could imagine those points in space living on that living on opposite ends of that long diagonal of a rectangular prism. I like to think about that like a shoebox. And what I'm really thinking about doing is trying to find that point right in the middle. And the way we do that is by saying, well, I need the x-coordinate to be right in the middle of the 2 x-coordinates. So I average them. I need the y-coordinate to be right in the middle of the 2 y-coordinates. And the same thing with the z's. And this is another example of something we saw before in the pre-calculus course. That's the midpoint formula for points in the plane. All we need to do is do the same thing in the z direction. So now we have a distance formula and a midpoint formula, and even better than that, they generalize from R1 to R3. If you want to find the middle of 2 numbers, average them. If you want to find the middle of 2 points in the plane, average both the x's and the y's. And if you want to do it in space, average all 3 of the pairs of things that you have. So there you go, distances and midpoints.